So we started looking at section 7.5, which is basically our last section where we're going to be doing lots of different identities. Okay, 7.4, we learned about 3 groups of identities: the reciprocal, Pythagorean, and the tangent and cotangent. In this section, we're learning about a couple other groups: the sum and difference. We're going to learn about the double angle in a little bit, and then the half angle. Okay, so these are all different formulas that allow you to take an argument that has something in it besides just the argument, right? It's got like a divided by 2, or maybe it's got like a times 2 for the angle, or it's got something where you're adding or subtracting inside the argument, and it gives you a way to get rid of what's complicated inside the argument. When you do that, it usually means that the entire expression gets more complicated, but the arguments in each part are very simple: just an alpha, just a beta. And sometimes you need the argument to be simple, even if it makes something else more complicated. You need the argument to just be straightforward. All right, so that's the tangent of a sum. Tangent of a difference is pretty much the same thing. It's just everywhere you have a plus, you make it a minus. Everywhere you have a minus, you make it a plus. But what I want to do before we even write down the tangent of a difference is I want to prove where that comes from. So the very first formula that I gave you, we didn't prove. But every other formula that we've done can be based on that one. All right? So let's start with this. And thinking about what we know about tangent, what's another way that you can write tangent using an identity from 7.4? Yep.
Sine over cosine?
Yes, you can write it as sine over cosine. And we already know all the sine and cosine identities. So we should be able to figure this out. So right now, if I asked you how to do the tangent of 15, and you didn't know the formula that I just gave you, you should be able to figure out the tangent of 15 based on doing the sine of 15, which we learned yesterday, the cosine of 15, which we also learned, and then dividing the 2. Okay, so you should be able to figure out tangent. But using this formula is a lot faster than doing sine over cosine. Okay? So we're going to figure out where that formula comes from so that we can just use that formula in the future. Okay, so let's start with sine of a sum. All right. When I break that up, does it break up into something that has my trig functions grouped, or are they mixed?
Grouped.
So sine of a sum. About Dex?
Mixed.
Yeah, they're going to be mixed. So this is the sine, cosine, cosine sine. So that's what we're going to start with. So sine, cosine, cosine, sine. All right. How about Nick? What symbol is going to go between them for the sine of a sum?
Minus.
It's one of those two. Those would be our 2 options.
It's for the top, the sine one.
The sine one.
Minus.
Let's try another guess.
Plus.
Yeah, let's go with plus. Remember, sine, we keep it the same. All right, we'll fill that all in a second. How about the bottom? Holly, can you tell me how the bottom is going to break up? Start with the trig functions.
The first sign is going to be alpha, and the cosine is going to be beta, and the next cosine is going to be alpha, and the next sign is going to be beta.
All right, so let's just the template. Don't even worry about the alpha and the beta right now. Just like do on the bottom what I just did on the top.
Oh, for cosines?
Yeah.
you mean?
Yeah.
So they're going to be grouped, so
They're going to be grouped, yeah.
sine and sine and
So which ones come first?
Cosine?
Yeah, we want to put the cosines first because it will make a difference in this one. So cosine, cosine, sine, sine. Cosine, cosine, sine, sine. And Nick, how about my symbol?
Minus.
Yeah, this time it's going to be the minus. All right. So now, and you started telling me, Holly, about the angles. What did you say the first one's going to be?
Alpha?
And the second one?
Beta?
Yeah, so it's alpha, beta for all of them. Yep. So alpha, beta, alpha, and a beta. Alpha, beta, alpha, beta. Okay, so we kind of can, since we know what it's supposed to be, we can kind of look at what the answer is going to be and compare it to what we have. Okay, we have two terms in the top, two terms in the bottom, and that's exactly what the answer is supposed to have. Two terms in the top, two terms in the bottom. All right, let's focus on this term in the lower left. It's a 1. So what I want to do then is let's make this term in the lower left a 1. And whatever we do to make that a 1, we have to do it everywhere else. And the hope is when we do it everywhere else, we automatically just get that as the answer. So let's see. What would I have to do to make what's in that box a 1? Yep.
Divide by cosine alpha times cosine beta.
Right. When you want to make something a 1, you divide it by itself. It doesn't matter what's in the box, right? So divide what's in that box by itself. But if you divide that by itself, you have to divide all 3 of these by what's in that blue box. Okay, so let's start to write all that down. So we got sine alpha, cosine beta. We're going to divide by what's in the blue box. So that's the upper left. Now the upper right, we have cosine alpha, sine beta, and we're going to divide that by what's in the blue box. Okay, now in the bottom, we're going to take the cosine alpha, cosine beta, and we're going to divide that by itself. And now we're going to take what's in the lower right, sine alpha, sine beta. Sine alpha, sine beta. And we're going to divide that by what's in the blue box. We divided all 4 of them by the blue box. All right. So as long as we do the same thing in all 4 spots, that's fine. Now let's go through each one. It's like we have 4 little problems, and we'll see what happens in each one. Does anybody notice what happens? Let's start in the upper left, right here. Yes?
Cosine beta cancel.
These cancel out. Yep. And what are you left with?
Sine alpha over cosine alpha.
And what is sine alpha divided by cosine alpha?
Isn't that 1? When we're picking out all base. Sine by its reciprocal. Not sure.
Yep.
Tangent.
That's tangent. Sine divided by cosine. So that's tangent alpha. There you go. All right, let's look at what happens in the upper right. Okay. What's going to happen in that part right there? Yep.
The cosines cancel out.
The cosines cancel out.
Simplifies to tangent beta.
And that's sine of beta divided by cosine of beta. That's tangent of beta. There you go. All right, tangent beta divided by, and then in the lower left, we're dividing something by itself, so we already know we're going to get a 1 there, minus, and what's going to happen right there? Yep.
You get tangent alpha beta, alpha minus beta. Because they both simplify down to tangent on
Yeah.
the parts.
Yeah, so nothing's canceling, right? We don't get anything to cancel, but you said, that what is this part turn into?
Tangent alpha, and the other part turns to tangent beta.
Yep, tangent alpha times, and this part right here
Tangent beta.
is tangent beta, and that is exactly what I wrote. So that's how you get the tangent sum formula based on knowing the sine and the cosine one. And how do you know the sine and the cosine one? Well, we proved those yesterday. So kind of building on what we did. Now the tangent of a difference, I can write that down. I'm not going to go through the whole proof. Basically, all that would happen with a difference is when you rewrite it, the signs would change. You would have a minus and a minus, and because the top one is a minus, it would cause that to be a minus, and because the bottom one is a minus, it would cause that to be a plus. Okay, that's all that would change. Everything else would work out exactly the same. Okay, so tangent of a difference is tangent of alpha minus beta is tan alpha minus tan beta over 1 plus tan alpha tan beta. Can I reverse? Yep, that looks good. So that's the formula for tangent of a difference. Any question on that formula? So now you can do all the same things you can do with sine and cosine. You can find the tangent of any angle that's a multiple of 15. We can do verifies. Let's try one. Now, we got to remember, with the tangents, you're going to get answers that are different than the sines and cosines. You're not going to get the root 6, the root 2 divided by 4 anymore. Okay? That's because with tangents, we have fractions other than root 3 over 2 and 1/2 that are going to come up in the answers. Still using the same coordinates, though, the 30, the 60, and the 45. But our answers could just be a little different. So let's try the tangent of, let's try a basic one, tangent of 15. Now, if you didn't know this formula, you could do the sine of 15, you could do the cosine of 15, and then divide the 2, but you're doing 2 separate problems. It's going to take longer. How can I rewrite 15? Yep.
Wouldn't that be tan 45 minus 30?
Tan 45 minus 30. Yep. So that's your first step. Figure that out. And now, plug in 45 for alpha and 30 for beta into the difference formula. So tan
45 minus tan 30
minus tan 30
divided by 1 plus tan 45 times tan 30.
Yep. That is how you get the exact answer for tangent of 15. All right, so now we got to kind of go through it. Let's start with our 45, 45. What's the coordinates for the 45, 45, 90 triangle? Yep.
Root 2 over 2, root 2 over 2.
Okay, root 2 over 2, root 2 over 2. Okay, we're not there yet with the 30, but we might as well write it down so we have it. Okay, what's the coordinates for the 30? Yep. 3 over 2, 1/2. So you're still using the same numbers, we're just going to get different results because we're not using sines and cosines. Okay. So tangent, what's the formula when you're doing tangent? Once you know the coordinate, what do you do with it? Yep.
It's sine divided by cos.
Okay, which would be, how would you relate it to this coordinate?
So it'd be x divided by y. Or not, y divided by x.
Y divided by x. Yep. Okay. So what's the tangent of 45?
1.
1. Yep. So you get 1 minus. Now the tangent of 30. Y is a half. X is root 3 over 2.
Can't keep it like that.
What happens when you divide those two?
The 2's cancel, so you get 1 over root 3, which you can't have like that. So you multiply by root 3 on top and bottom. So that's 10 here, multiply by 1. So you get root 3 over 3.
Yep. So that's 1 minus root 3 over 3. And at this point, you've done every calculation you need to. You can copy the rest from the top to get the bottom. 1 plus tangent of 45, you already did that, it's 1. Times tangent of 30, we already did that, root 3 over 3. All right. So trig is done. Now we need to just clean that up because that's an awful way to leave your answer. Well, first of all, since I'm just multiplying by 1, we'll start with that. All right, first, I'd like to clean up having fractions within fractions. What could I multiply everything by that would make it so I don't have any fractions within fractions?
Multiply by 3.
Yeah, multiply everything by 3. 3 over 3. And distribute that 3 out. So that's going to give you 3 minus root 3. And in the bottom, what would you have?
3 plus root 3.
3 plus root 3. Okay, that's better because now at least you don't have fractions within
Now you
fractions.
have a root on the bottom. which you can have.
Now we have a root on the bottom that we'd like to get rid of.
You have to multiply by root 3 or root 3 over root 3.
Does anybody remember what we multiplied by here? This is something we've used this trick a couple times. We used it with complex numbers, and we're going to use it right here. Yep.
The negative reciprocal.
So that has to do with like slopes of perpendicular lines, opposite reciprocals. We're not going to use that here. But there's a name for the thing. Well, what are you thinking you're going to multiply top and bottom by?
The reciprocal. Or the
Can you tell me what you're, I'm just trying to see if you're using the wrong term. Tell me what you would actually use for numbers. Like, what would you do?
multiply the top and bottom by 3 plus root 3.
Okay, no, not 3 plus root 3. Yep.
3 minus root 3.
You want to multiply top and bottom by 3 minus root 3. And does anybody remember what that's called? We changed the sign of what was in the middle of the two terms. Begins with a C. It's the
Conjugate.
conjugate, yes. So the conjugate is just a trick that will generally clean up like having imaginary numbers in the bottom. It will clean up having roots in the bottom. We're going to have all kinds of roots in the top, but that's fine. So now let's FOIL that out. Okay, let's do the bottom first. Okay. 3 times 3 is going to give me 9. What's 3 times negative root 3? And then combined with a 3 times positive root 3?
0.
0, right? That's negative 3 root 3, positive 3 root 3. And what's root 3 times negative root 3?
3. Or negative 3.
Negative 3. There we go. Very nice number in the bottom, 6. Top's going to be a mess. That's fine. Okay, so 3 times 3 is 9. I have 3 times negative root 3. So that's a negative 3 root 3. And then I have 3 times negative root 3 again. What's a negative 3 root 3 combined with another negative 3 root 3? Yep.
Is that negative 6 root 3?
Negative 6 root 3. And then negative times negative is positive.
So that's plus 3.
Plus 3. So now let's just clean up what we have there. So bottom is 6. What's 9 plus 3?
12.
12. Minus 6 root 3. So no fractions within fractions, no roots in the bottom now. But there is one more thing we can do.
Oh, we can reduce.
Yeah, what's everything that's outside the roots divisible by?
Isn't that divisible by 6?
Divisible by 6. 2, 1, 1. So final answer for tangent of 15, completely cleaned up, would be
2 minus root 3.
2 minus root 3. Yep, that's the cleaned up answer for tangent of 15. There is a little bit more arithmetic because remember tangent involves dividing, so you naturally have more fractions. Now let's check it. All right, so if we type in tangent of 15, and then I type in 2 minus root 3, I get exactly the same. So that's what I'd be looking for on a test. Okay, any question on that one? Okay, so a few steps there to simplify, but it's more, I'd say this problem has a lot more arithmetic in it than it actually has trig. There's a lot more arithmetic steps. The trig part is really one step. You just plug all that into your formula and then you're done. All right, so that's how you do tangent of 15. And doing any other multiple of 15, you're going to end up with a lot of these same numbers. Root 3 over 3's, positives, negatives, and 1's. Because usually when you rewrite something with a 15, one of the numbers is going to be a multiple of 45, the other one is going to be a multiple of 30, and the 45 one always comes out nice with tangent. It either comes out to a 1 or a negative 1. It's the 30, it's the multiple of the 30 that is not going to come out nice. Okay. All right, so that's tangent of a sum and difference. All right, let's look at this. This is another slightly different issue we could have with the argument. It's not that we have something added inside, now we have something multiplied. Okay? So we know how to get rid of something added or subtracted inside a trig function. We have sum and difference formulas for every trig function you need. Now we gotta look at multiplying. So my first question is, could we just take the 2, put it in front, and say, oh, we're done. We got rid of the 2 inside the argument. Does that work? Jack, what do you think?
No, I don't think it will work.
No? Do you know why it wouldn't work?
Not right now.
Anyone think they know why that doesn't work? And usually I try to relate this to thinking about it a certain way. And I did this yesterday when we started the sum and difference. Yeah?
Is it because the first one's a horizontal shift
It's a what?
and a horizontal stretch,
Mhm.
and then the other one is a vertical stretch.
Right. Just from a transformation perspective, they're not even the same. Right? That's horizontal stretching or shrinking. That's vertical stretching. It's not the same thing. So no, you can't just take the 2 and put it in front. That doesn't work. So if you can't take the 2 and put it in front, then what can you do with the 2? Well, let's look at this. Can somebody give me a different way to write 2x? And by writing it the way I'm thinking, it's going to connect it with a formula we already know how to do. Yep.
That's complex.
Yep, right, it is x plus x. Now, what formula is this right here now? Yeah?
Sine alpha plus beta.
Yeah, that's the sine sum. It's just a sine sum where the two angles are exactly the same. Right? So let's see what happens if we do that up. Okay, so sine sum, are we mixing the trig functions or grouping them?
Mix.
Mixed. So sine and a cosine, and then a cosine and a sine. How about my symbol between them? Plus or minus? Yep. Plus, we copy it down, and now fill in your angles. X, 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 X. They're the same. What do you notice there?
It's just the same thing.
It's the same thing, right? That and that are the same. So what would you get when you combine them together?
Sine x squared cos x squared. Or
Well,
sine-
we're combining them by adding them. So it's like xy plus yx.
Oh, you get 2 sine cos, or sine x cos x.
Say it again.
2 sine x, 2 cos x.
What would you get if you added xy plus xy? What would those two add up to?
2xy?
That's 2xy.
Okay, so it'd be 2 sine x cos x.
Yeah. It's 2 sine x cosine x. That is how you get rid of a 2 inside of a sine function. It's 2 sine x cosine x. Okay, and because multiplying by 2 is something that happens a lot inside the argument, there's a special name just for doing that, and that's called a double angle identity. So a double angle identity is specifically used to get rid of a 2 inside the argument. Now, if you have a 3, they might have formulas for triple angles or for quadruple angles, but you really can take a problem that's not a 2 and break it down so it is. Okay, and we're going to do that. Okay, so there's our double angle identity for sine. It takes an argument that had a 2 in it and turns it into arguments that no longer have a 2. I don't want to go through proving all of them. I'm going to prove another one, but it's going to take me forever if we prove everything. So this is the double angle formula for cosine, which again I could prove to you by doing cosine of theta plus theta, just like we did the last one. And if you simplify what you get using the cosine of theta plus theta, cosine sum, you will get that. But what I want to look at is a different way that we can write this. There's actually 3 ways you can write the cosine double angle formula. With the sine double angle, there's really just one. I've never really seen it used in anything other than this way right here. Does this kind of look like anything we've done before? It's not, but it looks kind of close to it. Yep.
It looks like one of the equations with the Pythagorean. Not the Pythagorean, not the
No, it is a Pythagorean.
Oh,
Yeah, it looks similar to that.
The equations on that list.
Yeah, does anyone remember what Pythagorean identity that looks kind of like? Yep.
Cos squared theta minus, or no, plus sine squared theta is 1.
Right. That's very similar, but it's not, to sine squared plus cosine squared equals 1. Okay, based on that, what would cosine squared be? Yep. Okay.
1 minus sine squared.
Yeah, 1 minus sine squared. If you make that substitution right there for cosine squared, you will get a different version of this formula. Okay? So I'm going to just do that off to the side, and then I'll put the answer right below it. So instead of cosine squared, substitute in this identity. 1 minus sine squared minus sine squared. What does that simplify to? 1 minus sine squared minus sine squared. Yep.
1 minus 2 sine squared.
Yep. 1 minus 2 sine squared. Now there's a third way I could get the formula. I'm not going to do that one. But it would just be, instead of solving for cosine squared and plugging it in here, you could solve that identity for sine squared and plug it in there. So again, we're not going to prove that third one, but you could prove it just as easily as the one above it. Okay, sine and cosine are the most important two. If you kind of noticed yesterday and today, we spent most of the class yesterday, in fact all of the class, on sine and cosine. And we didn't spend that much time on tangent. We did one question and we moved on. Okay, so sine and cosine are the most important ones. But if you had to do a tangent, right now you don't know the formula, how could you think of tangent using the formulas you already have?
Sine 2 theta over cosine 2 theta.
Right. Okay, you could do it as sine 2 theta over cosine 2 theta. Or, if you know this tangent formula, you could use that. So what would this do? Well, the double angle formulas basically give you more options. They give you different ways to figure things out if you get stuck using a sum or difference identity, or there's something you can't remember how to do. Right. So let's take, for example, let's do something numeric first. Let's say I want to figure out the sine of 60. Now, again, that's an easy one. You should know how to figure out the sine of 60. But let's say for some reason you can't remember it, but you remember how to do 30. If you know how to do something that's half as big as what you want, you can figure out what you want. Right? So let's figure out the sine of 60, pretending like we only know how to do 30. Right? How can you rewrite 60 in a way that it uses a 2 inside the argument? Yeah?
You just do 2 times 30.
Right, you could just do 2 times 30. Now again, this is not something you should ever need to do. I'm just kind of showing you how the formula works. There's other things you should know how to do with that. Okay. So we don't know how to get 60, so we're going to break it up into 2 times 30. That's 2 times theta is going to be a 30. 2 sine 30, cosine 30. Okay. 2 sine 30, cosine 30. So now, before we keep going, let's just put this off to the side. What is the sine of 60? We should know what that is. Sine of 60 comes out to, think of your circle, coordinate. Yep.
Root 3 over 2.
Right, we're going to get root 3 over 2. Okay. Again, you forgot how to do that for some reason. Okay. So let's keep going with this. 2 times sine times cosine. Here's your 30, right there. There's your coordinate. What's the sine of 30 degrees? Yep.
1/2.
1/2. And what's the cosine of 30?
Root 3 over 2.
Root 3 over 2. 2 times 1/2 cancels out because 2 times 1/2 is 1. And you end up with just root 3 over 2, which is exactly what we were looking for. Okay, so what the double angle formulas allow you to do numerically is if you know how to do something, if you know how to find an exact answer of an angle, then now you know how to find the exact answer of double that angle using any of these formulas. So now you can get exact answers of anything you want doubled. And more importantly, we can use it to simplify something like this. Okay, rewrite that in terms of sines and cosines. Is there any part of that that the argument is okay, meaning it's not complicated because the argument is just a single letter by itself? Yeah.
Would be cosine x.
Yeah, cosine x is fine. You don't have to change that. It's already a single argument. There's no number added to it. There's no number multiplied by it. Leave it alone. Okay. But the second one, that one's not good. How can we rewrite sine 2x so the argument does not have a 2 in it? Yeah.
Would be 2 sine x cosine x.
Yep, 2 sine x cosine x. And technically, we've done what they wanted. But let's say they asked us to factor it. What can you factor out from each of those terms? What do they each have in common? Holly? Well, x isn't a term, though. That's an argument to a function. So when we factor something out, it has to be a factor within the term. So the factors you can choose from are 2, cosine x, and sine x. Those are the only factors involved in each term. Yep.
So let's say 2.
Okay, 2 is a factor they both have in common. But there's more. Yep. Cosine. So we can factor out a 2 cosine x. And what would that leave me with in parentheses if I factored out 2 cosine x from both parts?
Sine x.
No, if I put sine x back inside here, and then I distributed 2 cosine x times sine x, I would have lost this term. So we have to put something in here so if we distribute back out, we get 2 terms back. So that means you need 2 terms in here. Yep.
1 plus sine x.
Yes, 1 plus sine x. So that's the factored version of what's up above. And we got rid of all the things that were complicating the argument. In this case, it was just a 2. Any question on that? All right. So having a 2 is easy. Right? You have a formula, you can directly look up how to get rid of a 2. Okay, now I'm not actually going to solve this problem. I'm gonna stop when we get to the point where you see it would become a quadratic equation, because solving it from there is what we do tomorrow. Okay, but let's talk about that equation. That's going to be a little bit hard to solve because it has a 2 and a 3. I'd actually like to kind of do one that has a 2 and a 2 rather than a 2 and a 3. Let me see if I can find one. Now, I don't want to solve and do a 3 at the same time. So you know what? Let's just practice writing cosine 3x without a 3. That's all I want to do for now. Okay, so let's practice rewriting cosine 3x. It's going to be too much to do solving and that at the same time. Okay. Do we have a formula for a 3x?
No.
No. then we need to break down 3x somehow so we can use the formulas we do have. I'm not really as worried about the 2x. I know we could do that. We already did that. But how can I break down 3x so that it would work with the formulas from the other page? Yeah.
Could you do cosine 2x and cosine x?
Well, we want a single cosine, but what would you want to put inside it? It's just got to be something that we can somehow tie it in with formulas we already have. Yeah?
Cosine of 2x plus x.
2x plus x. Yep. The higher that number is, the worse the problem gets. 3 is not bad. If you had something like a 9 or an 11, that starts to get pretty bad. Because what you have to do is you have to keep breaking off 2x's. You can't break off anything more than a 2x at a time. So if you had like an 11x inside here, you'd have to write it as 2x plus 9x. And you would have broken off one 2x. And you're going to do what we're about to do, but you'd have to keep doing it over and over. Because then you'd be left with a 9x, and you could break off another 2x, and that would get you down to a 7x. And then another one would get you to a 5x. This one gets us pretty much where we need to be right away. We're going to have to break off this 2 again at some point, but at least it's now down to a 2. Okay, so that's a cosine of a sum. Cosine sum. Do we group the trig functions, or do we mix them? How does that work? Yep. Yep, we're going to group them. Cosine, cosine, sine, sine. What symbol is going to go between them when we do the sum? Remember, it's a cosine. Yep. Subtraction. And now fill in your angles. 2x, x, 2x, x. So the thing that happens is when you break something down with a sum or difference identity, you turn it into from one problem into 4 problems. So that's why if you had to do this many, many times, everywhere that you have something that's not an x, you have to keep working with that more and more to break it down. Luckily, it's already down to a 2. So we have a formula we can directly use for both of those. Let's start with cosine 2x. How could I rewrite cosine 2x? Yeah?
Cosine squared x minus sine squared x.
Yeah, there's some options. It depends what we're trying to do. If my directions were to just rewrite it without a 2, you could pick any of those 3 that you see. But sure, we could do cosine squared minus sine squared. And so this becomes cosine squared minus sine squared times cosine. And then minus sine 2x, we did that earlier, 2 sine cosine times another sine. Right, and we could, let's see, we could simplify that a little bit. All right, so let's finish up where we were. We were pretty much done. The only thing I was going to do is multiply sine times sine. So that would have finished that. So the first part, I'm just going to keep it factored rather than distribute the cosine back in. And in the second part, I'm just going to combine, multiply together the sine times sine, and that would give me sine squared. And then, I mean, how much more you keep manipulating that, I guess it depends on what you're trying to do. They both do have a cosine in common. That has a cosine, that has a cosine. So you could factor cosine out of the whole thing. Maybe I don't know. It depends on what you're trying to do. But if your goal is to rewrite it so that there's no more 2's and 3's in front of the argument, we've definitely done that. So that's all I wanted to do with the 3x. Okay, show you an example of how you get rid of a 3. 3 is the highest number you'll have to deal with. Or maybe a 4, but we wouldn't have 5 or higher. It starts to get pretty big. All right. Any questions on that one? All right. So the double angle formulas allow you to basically figure out double, the exact answer of double any angle that you know how to do. The half angle formulas allow you to figure out the exact answer for half of any angle that you know how to do. So what that would technically mean is if you know how to find the sine of 15, you could find the sine of 7.5. You could figure out half of that using these formulas. Okay. What these formulas also do is they give you a different way to figure out one of the first problems we did, which was like, I think it was cosine of 15. Right? If you know how to do cosine 30, you can find cosine 15 without using any of the stuff I already showed you. You could do it using this. Okay, I think cosine of 15, I want to say it was like root 6 plus root 2 over 4. I think that was the answer. You could get that same answer using these half angle formulas. Just write 15 as 30 divided by 2. And 30, you know how to work with from the unit circle. Okay, so that's a half angle formula for cosine, sine, and there's also one for tangent. Okay, I don't really spend a ton of time on the half angle ones. They're not ones we're going to focus on very much. Okay, but now you know, or at least I've taught you, all the different identities that we're going to be learning. Okay? The reciprocal, tangent and cotangent, Pythagorean, sum and difference, double angle, half angle. Okay, and are there more? Yeah, there's thousands of them. There's tons of identities. But these are the most common ones that you would come across. And usually, like if you take calc, like when you flip either like the inside cover of the calc book and the front or the back, a lot of times they put all of these identities. Because generally the more complicated identities, especially some of these, I don't remember them. The goal is not really to have to keep memorizing an endless amount of them. It's more of applying how to use them. Right? The fundamental ones you should know, but some of these other ones, if they're not used as much, it might be something you look up when you need to use it.
So it's more like oh, I remember how to do that, not the, I don't remember the formula exactly.
Yeah, yeah. Like if somebody asked me to find the tangent of 7.5, yeah, I could do it. Did I remember that off the top of my head this morning? No. Now that I could look that up, I could go through and do it. Yeah. Okay. Any questions on those? All right. So let's take a look at the homework. Do so 18, 19. One. Change another one of those. 45 is a verify. That's a review question from yesterday. And let's just take out that one. Bless you. And let's try that one. That's a tangent one, so 22 might be a little bit harder, but it only has a number that's a 2 in it. So actually, if it was a 3, it would be hard, but no, it's only a 2, so that's actually fine. Okay, so 18, 19, 22, 37, 41, and 45.